I'm going to come back to that. Let's talk a little bit more about this off-grid case study. Um, all we had to go off of for the design was the client's month-to-month electric bill. And this is actually for their old house. So we had to go and look at, the big difference was their old house was on a electric water heater, and the new house has a wood-fired water heater with an electric assist. So there's a little bit of massaging we had to do to this. But what we got is the month by month energy use of the house. Now, under a unlimited net metering policy, we would look at all this consumption and say, okay, this home needed 17 megawatt hours, or 17,100 kilowatt hours of electricity. So 17,000 divided by 1.4, which is the golden ratio of solar performance, 1.4 kilowatt hours per watt per year. And what that would tell us is, we need about a 12 or a 13 kilowatt solar array, maybe a 14 kilowatt solar array to completely zero out this client's electric bid, assuming we had unlimited net metering. But that's just if we wanted to get, where the daily average production of the array met the daily average consumption of the house. But in off-grid, we're not going off of annual averages. I mean, what we can see is we use a lot more electricity in January and February than we do in March and April. But we get more power out of our solar array in March, in the summer and the fall than we do in the winter. And so wintertime months can be quite problematic in off-grid design. And likewise, you have to be cognizant of your summertime months too, because, while your array may be nice and productive in the summertime, you may go through a storm cycle where you get, 4 or 5 days of rain all in a row. And that's another danger where you have high air conditioning use and low solar production. You might have to be a little smarter. We could have had a much smaller array if the client said, in the summertime when it's overcast, I'm going to have an air conditioner that's going to run at 2 degrees higher than normal and do energy management and lifestyle adjustment. This client wasn't going for lifestyle adjustment. He has a wife and 2 kids in middle school. He's a doctor. He wants to live in an off-grid house. And he doesn't want his wife and kids to be like, what are you doing to us? This is terrible. Why can't we just live in a regular house with normal electricity? He wants a house. He wants not having to mess with things. And so what does that mean? Well, in July, if we went with that 14 or 15 kilowatt solar array, what we see is for this month of August, we need to do all the way up to a 17 kilowatt solar array to zero out our month of August. In April and May and June, you don't need a large array to zero out your bill. But you do need one in the summertime. And then also in the wintertime. In the wintertime, we're using a lot less energy in Mississippi than we do in the summer, but the days are shorter. And so instead of going with, and then we have to apply a little bit of a safety factor too, because, we remember if we're sizing off, making sure our monthly average equals our monthly production, we still have to account for the fact that there's weather and storm cycles, so it's not all evenly distributed. And so for an off-grid array, if you were grid connected, you might only need a 14 kilowatt array to net meter your home, and that same home needs to have more like a 22 to 23 kilowatt array for it to be off-grid and being able to be fully powered by a solar array. So to go off-grid with solar, your solar array really needs to be twice as large. Now, you could say, well, can't I do some energy management in the summer? Sure. And you can say, well, in the wintertime, can't I run off a generator? Yeah, you can do that. There are ways to get some of that sizing back. But now that solar modules are so cheap, generally by the time you actually start getting into that, you're really gonna want to overkill it with DC no matter what you do. In our case, our off-grid array is going on the guy's garage. It was originally a two-car garage with an extra space, and it became a three-car garage with an extra space because we needed the roof area for this larger array. Let's see. Battery systems are more functional. As far as AC coupling and DC coupling go, you can actually kind of mix and match it all together. The main rule is it's when you want to have one battery inverter, or at the very least one battery inverter manufacturer. So you can double stack and triple stack and quadruple stack battery inverters, but you want the battery inverters to all be the same. You want that communication, that digital communication. You don't necessarily need it between the inverter and all the other renewables on site, but you want the battery. You can't have two master battery inverters. You need to have one master and one, driving the whole system. So you could have 3, 4, 5, 6 different battery inverters on the same site. They all have to be the same brand. We talked about generators. Your generator lines now will actually have generators that are specifically built to be compatible with renewable systems. As far as I can tell, that's just to make sure that the generators are controllable by third-party control units. So on these like float, absorb, bulk charts, the way that you read them is you take, how much energy you expect to consume on a daily basis. And you look at, what I would do is I'd take the storage capacity of the battery bank and then subtract out each day. If I have a 120 kilowatt hour battery bank, and then each day I'm discharging it with 48 kilowatt hours, and then charging it with around 48 kilowatt hours all the way back up to the top, there's actually a way to map that out, and we'll show you that in a minute. But eventually you determine what is the average daily cycle of my battery. And if I'm doing a 120 kilowatt hour battery and I'm cycling it by 48 kilowatt hours a day, that's going to be kind of like a 45% cycle on a daily basis. And so if I'd say, okay, I have a 45% deep cycle, and that's going to give me 3,000 rated cycles out of my battery. And so 8 times 365, it's going to last about 8.5 to 9 years. Or I could double my battery bank. Instead of doing a 45% deep cycle, I could double it. And now I'd only be doing more like a 23%. And now my battery bank would last, 4,800 cycles. It might last 11 years instead of 8.5. And what we can see is that there is kind of along this absorb range, you really want to size it so that you're getting right down to the bottom. That's where your sweet spot is in terms of cost effectiveness. Once you start getting further into here, now you get into even more diminishing returns where you're cycling it deeper, and then you're not getting nearly as many total cycles out of the battery for going deeper into that curve. That's how you can kind of read battery charts. Now, it has to be taken with a grain of salt because these charts do not reflect how the battery is being used in the field. And so you'll often get discharge rates for lead acid, saying this is what it can provide at 20 hours of constant use. This is what it can provide at 5 hours at constant use, and it has to do with how quickly the battery is being discharged. There's also impacts of temperature. Now, I like putting my batteries in a temperature regulated environment, but you can't always do that. And so temperature and the speed of the process, solar is going to charge a battery in a period of about 4.5 to 5 hours. So it's going to charge at the 5-hour rate. An off-grid solar battery might be used for the opposite, 24 hours minus 5. An off-grid solar battery might be used for 19 hours. And so if you have a very controlled energy load that's at a constant level for those 19 hours, your battery is going to be discharging at the C20 rate. But if you have a tankless water heater and you run it for 1 hour, it might be discharging at a C1 rate, something very much more quickly. And so, really what we want for kind of off-grid design is flat use, or use where you have a larger load during the middle of the day when solar is on. And that works really well in the summertime with your air conditioning loads, but it's not so hot in the wintertime with your heating loads. And so there's this whole area of expertise that says, well, do we need to rethink solar design fundamentally? A south-facing solar array is great, but a north-facing solar array is almost equivalent in the summertime on the north side of the house because it matches up with the load. And maybe in the wintertime, an east-facing array, which economically doesn't make much sense. Usually if you have a time of use rate, it's the evening that has a higher rate. But to an off-grid homeowner, you may want some modules facing east just to get that morning draw off of the batteries. For that matter, you might want some modules facing west. It may be that an east-west array is the better design for off-grid than south only. What's neat about this stuff is this is Aurora Solar, and they're not, they don't actually know what the load profile is for your home. Sometimes you can get this data from your utility. You always can at the commercial level. They may not track this data at the residential level. But what Aurora Solar is doing is you're actually answering a little survey of what appliances are in your home and then putting in your month-to-month usage plus your location. And so based on what part of the country you're in and what electric appliances you're using, it takes your electric use and then just applies a load profile on what it thinks you will do. Or if you log into your utility account, you may be surprised. The smart meter technology enables utilities to give you this data even at the residential level. Now, I didn't have this in my off-grid home design, but I realized that my parents lived in a very similar house to the one that this doctor was building. And so I went and they're in a similar geography, maybe one that's a little bit more extreme. And so I looked at their, peak usage of their home. Their home, the service panel, electric service panels are way oversized at the residential level. They can do all the way up to 48 kilowatts of power. And that's, that's a lot. My parents' home doesn't get up to 48 kilowatts of power. It's maximum. They live in Tulsa, Oklahoma. They get hot summers. Its maximum power draw in August was 15 kW, and it's because it's just the two of them living there. They have a large, energy inefficient, kind of gas guzzler of a home, but it's not like they're running all 5 burners of their stove plus the air conditioning and all their lights, incandescent light bulbs all at the same time. And so anyway, this gave me confidence that we really only needed about a little over 14 kilowatts of power out of the battery inverter to give this doctor the same standard of living that he expects from his existing home. And so looking at the product lines, we had a choice between like 2 5.5 kilowatt inverters And the battery inverters have a burst mode. So a 5.5 kilowatt solar inverter, that's its maximum output. On the battery inverter, the 5.5 kilowatt could provide 7 kilowatts for 30 minutes. And then it can provide even more than that for like 1 or 2 minutes. So actually, those tankless water heaters, a battery inverter can handle it. It's just that for a lead acid battery, yeah, you can't discharge lead acid that quickly. That might be a reason to go in with lithium ion. Instead, we went with a slightly larger inverter, 7 kilowatts instead of 5.5, and that gave us a burst mode of more than we need. But on top of that, our inverter has a generator module so that, on New Year's Eve, when you're using, all of the ovens and stovetops and you're watching the big game and staying up all night, you can turn the generator on too, or the system can automatically turn the generator on and give you that extra, 15 kW to 25 kW of power if you absolutely need it. Which during those times, you're going to be wanting to charge your batteries up anyway, so the generator is probably going to be on anyway. So when we evaluated inverter selection, the main deciding factor was which battery inverter was set up for 600 volts. Most solar inverters are set up for 600 volts. When I started evaluating the battery inverter market, I was shocked because most of these battery inverters only had the charge controller, that voltage regulator between the array and the battery inverter, only went up to about 150 volts. I'm like, this is strange. A solar circuit per National Electric Code can have 600 volts. These only have 150. There's usually 8 or 9 modules a circuit. Does that mean battery arrays only have that are DC coupled only have circuits that are 2 or 3 modules in length? And the answer is yeah. These off-grid hobbyists, they're not trying to power, a suburbia-style home. They're trying to power a very minimal energy use home. And, they have smaller arrays and smaller stuff, and it's all hands-on, and it's all ground mount. But our off-grid system's going on a rooftop. And so we can't have, every 3 modules, another circuit. That's just, tons and tons of wirings. We have 8 rows of 10 modules each, and that would mean we'd have, dozens of circuits on a rooftop. It's just too much wiring. So ultimately, we picked our inverter because it was the inverter that had the most market experience with 600 volt charge controllers, and that allowed us to have a nice long circuit up on the rooftop, and so that was kind of an eye opener. That most off-grid DC coupled systems are on little 150 volt circuits with short little tiny circuits, not like the longer circuits I'm used to in solar. So we would have had to have, if we went with, kind of the best reputation charge controller on the market, we would have had 32 solar circuits up on our rooftop. Instead, we went with another very good one, and now we only have 8 circuits on our roof. And that's all because I'm trying to get rid of stuff on the roof in my design nowadays. Anytime I have to get up on a roof to maintain a system, all I can think about is how unenjoyable that process is for everyone involved. As if you're on a roof doing solar, you want to be doing a project. You don't want to be doing maintenance. So we evaluated Schneider, SMA, Outback, Magnum, Morningstar, and then a Portland, Maine startup called Pika that has some interesting attributes about it that we really can't get into in class. And I'd say in the U.S. market, it's kind of funny because, Outback has the best reputation amongst solar installers in the U.S. market. SMA kind of drugged their feet a little bit on the US market because the SMA battery inverter is 120 volts. So they had to get a transformer integrated into their product and go into UL listing. And it just took them a while to figure out if they were going to make this product for the US or not. And so SMA still has its quality, stellar reputation. And I know many installers who would say for a battery system, residential, go with SMA because it's very kind of simple and easy. Outback gained a lot of goodwill and market reputation. Schneider bought one of Outback's competitors called Xantrex. And if you actually go back to Xantrex and Outback and Magnum, all of these companies come from one inverter company called Trace Inverters, whereas SMA came from Europe. So Schneider, Outback, and Magnum all have pretty similar offerings. SMA is a little bit different. I really don't know too much about Morningstar other than it had a good reputation too. And they also had a 600 volt charge controller. So, what we looked at is who had a 600 volt charge controller. Most all of these systems are expandable. Magnum was a little bit less expandable. And so what I mean by that is Magnum has a choice where you can either go from a battery bank or the grid. And it's a little bit cheaper, and that's because it only has either or. What, say, the Schneider inverter will do is let you switch between the grid and a battery bank, or between the grid and a generator and a battery bank, whereas the Magnum's a little bit more limited, which makes it very popular for off-grid communities where budget is an issue, where you still need a high-quality battery inverter, but you absolutely know you're not going to connect to the grid. Magnum's fine for that. Personally, I went with a Schneider, even though it was an off-grid home. Some installers say, well, that's fine because you could have two generators, a small, quieter one, and then a large one for when you really need it. What I think is down the road, you could add additional batteries that way, and some installers have looked into that, where you have an off-grid micro community where you still have a grid feeding the homes during the day. For me, I went with Schneider because it had that grid versus generator option. Just because if the good doctor gets mad with his off-grid home, he could bite the bullet and grid connect it if he really wanted to. So a little bit of insurance there. Schneider's a big company. A lot of these companies are pretty big. And so, we went with Schneider, and I felt pretty good about that. I know that Schneider went through kind of a reputation issue when they bought Xantrex, but that was in years past. We're way beyond that in the industry today. So anyway, another thing for off-grid, we went with 2 inverters instead of 1, and then you have to look in, okay, well, are the inverters bypassable or not? Often you'll buy a manufacturer-provided service panel, not because you have to, but because they'll set you up with all the right kind of interlocking switches for facilitating auxiliary modes where you turn the whole array off, but you can still run on the generator for servicing and stuff like that. So these custom service panels are pretty expensive, but I think they're worth it. This is a service panel that I think is interesting because it has both an AC side to it and a DC side to it. So I've never seen that before. So as an AC bus and a DC bus, you're plugging in everything into it. You plug your charge controllers into it, your batteries into it, your solar array into it, and that might be on your line side connection between the utility service and the load. we went with a Schneider charge controller and a Schneider inverter because it just makes sense. You stick within the product line, you don't mix and match, so that when it comes to monitoring, everything can show up on the same central display. The charge controllers, each of the charge controllers had two inputs. And so we talk about like string sizing, where how many circuits go on which inverter. This Schneider charge controller has two circuits up to 600 volts each. And so what I did, because this is a pretty good design practice, for my cabling sizing, rather than do a voltage drop calculation or an amperage calculation, all of that you need to do, but you're going to want to upsize your cable, because the thicker your cable gauge, the more efficient the system is. In off-grid, even in grid connection, it's worth it to spend money on efficiency. And so what I did is I started with the terminal block that the solar circuits land on with a charge controller. And that told me, okay, we need to have two inputs, two circuits, and that means we're going to have 8 circuits on the rooftop. And then what's the cable size going to be? Well, the largest cable that they accepted was number 10. And so we went with number 10 cable going into our circuits, and that just kind of set the design from that point. Now, your battery inverter can handle multiple circuits of batteries, but there's a different problem with batteries in that you want the cables between your battery circuits to be the same length. If they're different lengths, then the current is going to be drawn out of parallel batteries differently from each other. And what that's going to do is it'll get one battery off from the other, and that'll lead to a degradation of one battery before the other degrades. And like a waterfall effect, that'll then put more load on the new battery or the better battery, and they'll degrade. In short, they'll degrade unevenly and quicker if these cable links between the batteries and the interconnection system are of different lengths. So often you'll see customers either stack them on a shelf and put the inverter service panel right next to it. You get out of some disconnect requirements if the run between these two systems is 5 feet or less. And what that means in a battery room is you might have 2 inverters here, and then your service panel, and then 4 charge controllers, and then a giant battery bank that might be 12 feet long. So the total wall of your room, it might get into being 20 feet long, or you could turn a corner or something like that. I guess when you call up Schneider, they'll say, well, you could actually do 3 circuits of batteries. And we see some installers doing 3 circuits, but 2 circuits is recommended and 1 circuit is ideal. There's a lot of power that's going to flow through those batteries to that inverter. So, you generally stick to 2 circuits of batteries in parallel. And so what we're doing here is, remember in our solar class, we said you could go into PV watts and you could extract the hour by hour performance data of PV watts. So we know each hour of the day what our solar array is doing. Well, now what we've done is we've taken our monthly electric bills and determined an average daily production for that month. And so here we have a 120 kilowatt hour battery bank. So we're starting off fully charged at 120 kilowatt hours. And then every day for the entire year, we're taking the daily energy consumption out of the battery bank, and then we're adding back in the daily production. So you can see in the springtime, our consumption is so low and our production is so high that the battery is just being, right at the top of the battery usage range. We're not really using our batteries all that much in the springtime. But in the winter, when you get stormy, cloudy weather cycles, you can see that we're operating down in the absorb range here. And then we might even peak below the absorb range, getting into that 60 to 65% deep cycle before we get enough sunny weather to come back up to the top. And then here we are in July, and normally in July we're okay. We have an average depth of discharge is greater than our average depth of discharge in the springtime, but we're still in that absorb phase, except right here, I live in North Mississippi. Maybe this was a hurricane in Louisiana. And while you don't get terrible weather, you don't get hurricanes that much in North Mississippi, you still get the cloud coverage and some days of rain. So this might have been where we gone from 1, 2, 3, 4 days of a storm cycle. And now what we see is that the solar array still can't really recover in the partly cloudy days to come. And it takes, over a week before enough sunny days are strung together to take our battery bank all the way up at the top. And then it happens all over again. And so you can actually model that in PV watts. PV watts will give you the number of overcast days in a row, which is phenomenal. And what we do instead of allowing that deep cycle lead acid battery or nickel iron battery to be fully discharged, instead we would take a generator and say, right when the battery is reaching the bottom of its absorb phase, turn the generator back on and charge the battery back up. And so it never gets into this period of deeper cycle. And so we actually use that metric. How many times would the battery need to rely on the generator to take it back all the way up to the top? We use that metric to compare a deeper cycle battery to a shallower cycle battery. So this 122 kilowatt hour, we were protecting at a 50% depth of discharge, but this nickel iron battery is rated for an 80% depth of discharge. And so we can actually do a smaller battery because it's rated for a deeper discharge without damaging it. And so lithium ion is the best at that because you can drain it almost all the way down to zero. And so you might think, well, since I can buy a smaller battery, does that mean I'm going to save money? Is it cost effective to buy a smaller battery? Well, again, it comes down to, well, maybe it is in the long run, but that also means you have to come up with a lot more upfront cost of capital. And the amount of money you need to spend to get the top of the technology batteries won't economically compare to FLA unless you're unwilling to do battery maintenance. But anyway, what I really wanted to say was we were able to hone in at around an 80 kilowatt nickel iron or kilowatt hour, 77 kilowatt hour nickel iron battery bank. We were able to hone in on that size because that was the size of the battery bank where it exhibited the same kind of generator usage as the larger lead acid. And because the homeowner had told us he didn't want to have to worry about the generator running all the time, we wanted to give him a battery alternative option, like the nickel iron option, that would give him a similar experience to what he would get at the 100 kilowatt flooded lead acid level. And so to have at an 80% depth of discharge rating instead of say like a 65%, he could only go so small before that lack of storage capacity kicks in. Likewise, we would have to do a 77 kilowatt or maybe a 70 kilowatt lithium ion battery bank. And so that kind of starts getting into where these numbers came from, where a similar generator usage for 122 kilowatt hour, a similar generator usage for a deeper cycle nickel iron battery, and even a little bit smaller for similar generator usage for lithium ion. Of course, the problem is you could always run out of gas. And so there are, the one problem, yes, lithium ion, as far as going off grid, your lithium ion battery for the same kind of user experience, it can be almost half the size of the flooded lead acid. And yeah, the cost of that lithium ion using the best pricing on the market, which is the Powerwall 2, and I don't even think that's really honest because it's hard just to go out and buy it. You're usually looking at maybe $500 a kilowatt hour or more, but let's just assume we're 6 months from now and we get better pricing. Let's just talk very generally and say the Tesla Powerwall is half the size of an equivalent lead acid, and it's also twice the cost, so that their budgets even come out the same, and their price per kilowatt hour is about the same. Of course, with Tesla, you wouldn't have any maintenance. And so you'd say, well, JR, isn't based off all of that, isn't lithium ion the better option? And the answer is yes. It's the better option for a grid-connected battery where you're quickly charging and discharging it, such as in a commercial application. Yeah, it's better for providing a little bit of power during emergency for residential because A, emergencies really don't happen that much, and B, we're providing a little bit of power at night and a lot of power during the day. It's not like we're doing a little bit of power the whole time. So it's not quite the generator experience, but we're almost there with it. But there is one advantage that even an equivalent cost flooded lead acid has, which it's really more of an off-grid advantage. And that advantage is if you need those extra kilowatt hours, you have them. Whereas with the Tesla Powerwall, once you need to turn on that generator because your batteries are fully discharged, once you need to turn on that generator, you need to. My customer could completely disconnect his generator and run just fine. Except he would more deeply cycle his batteries, and his batteries would conk out a little bit sooner. But if he went with that smaller lithium ion bank and the generator doesn't work for some reason, then he's out of electricity, and that's when you lose. That's when you go to jail without passing go. Is when your solar customers complain about one microinverter going offline. An off-grid customer is going to be very upset if they run out of electricity. So anyway, it actually turned out that July was our deepest cycle because of our high energy use. That's no problem. We can just actually do some energy management during those storm cycles to overcome that. Looking at some battery spec sheets, we got, it's kind of funny. We have a premium line, which is their recommended renewable energy battery. And then they have their intro renewable energy battery. And then they have their industrial line. But actually, you look at these batteries, and this is a 2-volt battery right here versus a 6-volt. But then they have some 2 volts. Basically, when you stay in this industrial line, you have a choice between a 6-volt battery at, say, let's use the the 20-hour rate. 6 volts at 464 amps or 6 volts at 700 amps. So these two batteries, this one's a little bit more premium than the other. You go and you pull open the spec sheet, this one's a little bit taller than the other one too. It weighs a little bit more than the other one. So it's really just kind of a larger battery. And then we see another 6 volt option that's even a little bit more robust. But then quite quickly, we had 3 6 volt options. Now we have a 4 volt and a 2 volt and a 4 volt and a 2 volt. And then you're at the end of the line here. And so remember, we need a 122 kilowatt hour battery bank. And one problem that I started to run into, so say, okay, based off the PV watts production, we need about a 22 kilowatt array. And then we look at the production of a 22 kilowatt solar array, subtract the consumption of the house, and what we need is a 122 kilowatt hour battery bank, because that's as large of a battery we need for lead acid to where we're not completely draining the batteries, and the system would work through your typical storm cycles without a generator. But we're going to have a generator anyway just to protect it. But don't worry, you don't need a generator. And this customer specifically requested that he not need to worry about a generator working or not. He's trying to be off grid to be free. He doesn't want to become trapped by worrying about the functionality of his system. Okay, well, what we're looking at here is a 2 volt battery, and the maximum 20-hour discharge rate is 1850 amps. And so what we're looking at is 2 volts times 1850 amps divided by 1,000. A volt times an amp is a watt. This battery is a 3.7 kilowatt hour battery if we're discharging it over a period of 20 hours. Now, I can only have 2 circuits of these things because, when you get into multiple battery circuits, you have that degradation issue because of different conductor lengths. And so what that means, if I have a 2 volt battery, most battery inverters are 48 volts. Now, the Tesla batteries, your lithium ion specific battery inverters may be operating at a higher voltage level. But, your Outback, Schneider, SMA, they're all 48 volt battery inverters. So you divide 48 volts by 2, and that means the maximum batteries per circuit, if we're using 2 volt batteries, is 24. And now that's going to be a pain in the butt to wire up 24 different batteries. On the other hand, if you went with a 6 volt battery that is 3 times as large as a 2 volt battery, it might get so heavy that you can't transport it without heavy equipment. And so, if you're going off grid and you want to avoid heavy equipment, you have to be in this 2 volt battery range. Otherwise, the batteries get too expensive to pick up. We went with 12 volt batteries for our off grid project. We have 8 of them, and they weigh like 600 pounds. They weigh 600 pounds each, and 6 times 8 is 4,800 pounds. And that meant that we couldn't get a lift gate because the shipping company's lift gate was too weak to offload the batteries. And so that means we had to rent some heavy equipment to offload the batteries from shipping. That's $800 right there spent on a piece of heavy duty equipment for one day. But then again, you do have to wire up all the batteries. But what I wanted to point out was, if you have 24 batteries per circuit and they're at 3.7 kilowatt hours each, that gets us up to 88 kilowatt hours. And if we had 2 circuits of that, that gets us up to 177. So, the top of the line from Trojan, which is a solar lead acid battery maker. Their top of the line industrial lead acid battery, does give us the power that we need to run the home off grid. But we're like at the tip top of their product line here. There's not much more room to spare. Eventually when we went through the entire bid process, we actually changed it up and we went with this Hawker battery. That's another industrial battery, but it was a 12-volt model, and we ended up going with this one right here. And so, sorry, the batteries weigh 800 to 900 pounds each. They're quite heavy. So anyway, there are some code requirements for working space. Basically you can't have other kinds of equipment in the zone of your electrical working space. And then the other big one the other big space requirement, I'm not sure if I illustrated it or not, but if you have two pieces of electrical equipment, so let's say this is your battery, let's say this is your battery bank right here, and you really wouldn't want to put a desk there. This is kind of an architectural drawing. Let's say you wanted to mount, let's say you're building a box, and the battery bank's going in a completely enclosed, protected box that's being off-gassed to the outside. And then you wanted to put in the space above the box some additional electrical equipment and conduit runs. What you run into is you're only allowed a 6-inch gap between the faceplate of your electrical products and the furthest extended electrical device that's on the same vertical plane. And our battery dimensions that we went with, they stick out from the wall by 38 inches, or they're 38 inches tall by 7 inches wide. They stick out from the wall by, I guess, 2 feet. And so, these are our batteries. Our batteries stick out 2 feet, and our solar equipment sticks out 6 inches. So we can't put our solar equipment like above the batteries on the wall. They have to be spread out for serviceability. And so that gets, if we have 8 of these batteries and they're 7 inches wide, that means we have 56 inches going into the batteries themselves. And that means we have over 5 feet going into the batteries themselves, and they have to be right next to. Do I have a picture of it? Maybe I have a picture of it later. Probably, yeah, here we are on the next slide. So we need 5.5 feet for our batteries, and we need 8 foot 1 inches wide for our 2 inverters, our service panel, and our 4 charge controllers to have everything look nice and neat. And we were designing this system, but we didn't take into account that it wouldn't fit if we had it all along the same wall. So we're actually kind of putting it along this wall, and then we're not putting this door here, and then we're turning the corner and putting the rest of the equipment there. So you need about, so we were barely able to squeeze it onto this this section here with and that would have resulted in a minor code violation because of the faceplates overhanging. So anyway, battery equipment can take up a lot of space and a lot of room. This is lead acid batteries are large and heavy. Anyway, guess I could have just shown you this slide. So let's kind of move on. Your batteries should be considered a damp location. Okay, so what we can see here in this picture is this is actually a code violation. because the batteries stick out, 2 feet from the wall and the panel only 6 inches. This array is actually code compliant because you do have that serviceability minimum depth of working space between the two. And then we see these little caps on top of the batteries to capture the gas and do some ventilation to the outside. Okay, so at the end of the day, we were choosing between two batteries, flooded lead acid, 122 kilowatt hours, or nickel iron, 76 kilowatt hours, 30-year battery versus an 11-year battery, 4,100 cycles versus 11,000 cycles, 16.5 cents a kilowatt hour levelized cost versus around 9 cents, and the client still went with the lead acid. Because he said, this lead acid battery is about all the money that I want to spend. The reason why the doctor was going on with this project is because the power company is charging him about $20,000 to bring power out to his property, where he specifically wants to build. And so his thought was, well, I would rather spend money on my own home than just give it to the power company. So if I'm going to do solar anyway, I have at least $20,000 to play around with for a battery bank. Furthermore, there's the tax credit, so more like $26,000 as my battery budget. And the nickel iron batteries, which would have lasted 30 years or too much, the concern is, well, doesn't that mean, halfway through project ownership, he's going to have to replace his lead acid battery bank? And yeah, you do. Lead acid batteries are recyclable, though. They do have some material value left into them. So, you might get someone, the lead acid recycling process is really well established. So you might get a solar installer actually picking up your old lead acid batteries just for their recycling value. Nickel iron is a little bit more hazardous. You need a hazmat permit to transport it, actually. Just some additional details about this case study while we're on the topic. We were on a standing seam metal roof. We went with a railless racking system, which actually did not turn out to save that much money. I would have thought that by eliminating the rail across the array, that would have been the bulk majority of your racking cost. The reason why we didn't make money is because your clips on a standing seam metal roof, they really have to go on every seam as you go across the rooftop. And so we're buying a lot more we're not buying the rail, but we're almost doubling up on our little attachment points compared to a regular solar array. And this is kind of a specialty part. And then we're using an all black module. So we had to get it black anodized through a third party so that it looked good. And so at the end of the day, the railless racking system didn't save us as much money as we thought. One technique that we've implemented, we're in process of building this right now, but one technique that we've already implemented is going into the rooftop on this metal roof. We went in through the Z-purlin, whereas the roof has a little bit of a gap at the top. You can see there's this metal piece of flashing put over the hood, but ours is a vented roof cap. And so we're actually running our cable through the Z-purlin and then into the roof. And there's some parts of code that are like, well, if you're boring straight through metal, you have to make sure that induction isn't going to heat up a ferrous metal. And there's temperature derating if you're below a half an inch below the roof deck, and it's pretty extreme temperature derating too. And then there's derating for number of wires in a conductor and all of that. So we had to take all of that into consideration. But normally an installer would run conduit along the side of the roof and down to the point of interconnection, or they'd penetrate through the roof, which for a metal roof is not particularly elegant. And so we just had to take a step back and say, now, wait a minute. Why can't we go through here. What's so different about that than a pass-through box? In fact, the roof cap fits nice and over it. So that worked out. So that saved us a roof penetration. That saved us, if we're really being honest with ourselves and we're doing things right on a metal rooftop, that saved us buying this whole little ugly vent or hood. And our budget, we got our solar panels for 50 cents per watt, all black, 290 watt, all black solar panels, 50 cents a watt. Spent 10 to 12,000 bucks on that. Our railless racking system actually came in at about $4,000. Panels came in at 10 grand. Schneider, this is $13,620 divided by 6.8 kilowatts divided by 2, divided by that oversized DC array. What we're seeing is 13,620 divided by 6.848 divided by, the DC side is oversized, and there's 2 of them. Let's see, that didn't work out. 13,620 divided by 1.2 divided by 6.848 divided by 2. Yeah, so when it came down to it, the Schneider inverters plus the charge controllers and all the distribution panel, the inverter, the auto start, the monitoring system that comes with it, ended up costing us about 80 cents per watt total. Whereas a residential batteryless string inverter going into a standard service panel, that whole budget might be 26 cents for the inverter and 5 cents for balance of system. So at the end of the day, by the time you rack up all the bells and whistles for taking a house and giving it 100% off-grid functionality, not only do you have to buy more modules, but you're also spending 2 or 3 times more on your inverter system. That's actually caused some inverter companies, I'm going to skip way up to the beginning of the program, that's actually caused some inverter companies to reevaluate their total system design. So this is Pika Solar. They're kind of a startup in Portland, Maine. And, what they're doing is selling you an inverter, and they're saying, hey, look, this inverter is not for off-grid. This is for a grid-connected battery inverter. But we're going to allow you to wire a small critical load panel to our battery inverter. So we're not going to do the generator. We're not going to give you tons and bells and whistles, but we'll give you the ability to power a little bit of critical load off of our battery bank. So in a 1 hour or 2 hour power outage, you're going to be perfectly fine. But you're not trying to show off how your home is your castle. It's not an impenetrable fortress, but you don't need to buy all the bells and whistles. And then they're combining that kind of, it's a battery inverter, but it's not intended for off-grid. They're combining it with not micro inverters, but string inverters. So instead of 1 module level panel electronic per module, 1 microinverter per module, 1 DC optimizer for every 2 modules. Now it's 1 box for every 8 or 9 modules, which is a more cost-effective microinverter strategy. And then they've created a battery control unit that can just be plugged directly in so that you don't need to get the battery now. You can get the battery, kind of later. So Pika is kind of interesting in that in that they identify that right now you spend a lot more on your inverter components, you spend a lot more on your battery components if you want to do off grid, and maybe all the off grid features of these expensive battery inverters are not necessary um, when it comes down to it. Uh, that grid connected customers do not need the same kind of battery inverter that an off grid customer needs. They could have something a little bit more simple, a little bit less expensive. So we're still in that evolving market. And it's to the point where Tesla thinks that they can just go and make their own inverter. That's how much you have off-grid battery inverters and then not much else. And generally the off-grid battery inverters don't even make grid-connected inverters. SMA and Schneider are kind of the exception, because their customers are more servicing the off-grid market. Well, now we're seeing that the grid-connected battery has more cost-effective applications than the off-grid battery, like in the commercial market. So, we might see some new inverter products come to market over the next few years. Let's see. Our balance of system material, $5,000. We're probably going to come in at less than that because the service panels included in this price. The battery bank we ended up getting it for about $22,500 as a result of competitively bidding it out. And then shipping's expensive. And anyway, I did my normal I designed the system. The client is actually self-installing the system, and so he's getting his off-grid 20 to 24. It's turned out to be about 22, and getting his 22 kilowatt system for about $77,000 plus the price of a generator. All in, it's about 22 kilowatts for a little bit under 80 grand, which means he's getting an off-grid home for 360 or 370 per watt, but his project is substantially larger than most solar scope. So anyway, we actually told him, look, you got two options. You could do the flooded lead acid battery bank, and that'll cost you $76,000, and then you'll get the tax credit that'll bring it down, and then you're going to save money by avoiding the interconnection costs. And so after the tax credit, after the cost savings on the interconnection, this system will cost you about 34 grand. Between the meter fees and your electric usage, it'll save you about $3,000 a year, which will give you an 11 and a half year payback, except right around that time, you're going to have to buy a whole new battery bank and start all over again. So this customer is one of those archetypical examples of a customer who's not really doing solar for the payback. He needs to get a payback. He wants a payback. But really, this customer, he wanted to do a 300 kilowatt solar array and sell the power back to the power company. But the power company, even though they had this program, they would not process his application. He's on a co-op, and the co-op said, we don't have the manpower to legally review your application. And that ticked him off. And then they come out with no net metering and this $18,000 bill. And it didn't take much for that doctor to say, I don't ever want to have to deal with you guys ever again. It's more expensive for him to go off grid than to grid connect, but solar array owners, some of them have very deep pockets. And if they feel like they're being slighted by the utility, maybe they are, maybe they aren't. But if they feel that way, some of them are going to go off grid now and be your early adopters in that market. If solar policy becomes too punitive against solar array owners, they will disconnect from the grid. And it's kind of a failure in our energy policy if we are encouraging the clean power generators to spend more money to grid disconnect and be less efficient versus to spend less money in Grid Connect and be more efficient. So, we need to have a policy that strikes a good balance to avoid discouraging customers from going off grid. At the same time, the vast majority of the off grid market is in areas where the electric grid doesn't really exist. And so the cost of grid expansion is so much that going off grid makes sense. And this kind of process, as compared to a nickel iron battery, it comes out to be about the same. He spends more money up front, but then he really only has to do some battery maintenance and not completely replace the battery. And so the payback time comes out to be about the same. So, when you keep in mind that many of your off-grid customers have deep pockets and there's some luxury motivations rather than economic motivations, a customer might pick the nickel iron battery simply because they don't have to replace it, unlike a lead acid. A customer might pick that top shelf lithium iron phosphate battery because they're Michael Dell and they're living in Hawaii and they want to make sure that their battery never conks out on them. There is a high-end luxury battery market. It's not the only market. There's that grid-connected commercial market too, and then there's just selling residential customers small little battery inverters with a small battery just to give them a little bit more functionality out of their array. What's really, to me, what's humorous about this entire project is that if we had grid connected, we could do a much smaller array, use a cheaper inverter. We could even still do the battery inverter so that he could still have some power during a blackout if he really wanted to. And that cost of grid interconnection, it's possible to get that cost written off. It depends on how you structure the project, but we could have built the project first, waited a year to build the house, and said the interconnection work was part of the array project, qualified for the tax credit. And so we could have done a small lead acid battery bank, 10 kilowatt hours instead of 120. We could have paid the price of interconnection, done a smaller solar array because we don't need it to be overproductive, still giving them that backup power security, and had the total project come in at 60 grand instead of 75, but he also has the security of the grid connection. And so it would have been less expensive for this customer to grid connect despite the grid interconnection fee. But he didn't want to do that. Another aspect is he's building in the middle of his property. The power lines actually go through his property on the edge, but he's building in the middle of his property. You have to go over a creek to get there. It's built on the only hill in Mississippi, so it has a really nice view. And he doesn't want to destroy that serenity by running some overhead power lines right across his scenic view. And so there's some additional motives here.